Okay, so maybe what I prepared is way too trivial. I have not. Please tell me if you have a strong feeling that it's way too trivial. It's probably, I'm going to 80% talk about stuff that 80% of the people here know, but I'm going to make some references to that are non-trivial, hopefully. But it's useful because we have a very broad audience. I think it's useful to just set some basic terms. So about the tutorials otherwise, so I will focus on mostly shallow machine learning methods and some principles and terms, but they also apply to deep learning. Then mostly I'll focus on supervised learning here. And Marina has a talk tomorrow, is that right, or today? About manifold learning, so that's unsupervised. Then tomorrow I will go into neural networks, some basic techniques, but then also some reference to like how to relate to physics. And then we'll add on to that. So Patrick has a talk on equivariance and invariance in neural networks that Cecilia briefly mentioned yesterday. Then Lars, where's Lars here, is going to relate to ordinary differential equations, and we'll talk about ResNets more. And then next week I will talk about generative networks and statistical physics. So if I recall correctly, this is mostly the ML methods part. And then we have a couple of talks on applications from different application areas like fluid mechanics, quantum mechanics, molecular dynamics. All right.
Do a feature engineering and data preprocessing stuff.
In your talk. Yep. Thanks. Okay. So, all right, let's start with something very simple, linear regression. Everybody knows that, hopefully, but it's useful to discuss some terms. So regression is a supervised learning problem. We have inputs and labels that we want to regress to. We have a training set with endpoints. Inputs are going to be called X, outputs are going to be called, or predictions are going to be called Y. And the I is just a sample that we refer to, or the data point. And we basically want to make a prediction Y hat based on the inputs and some parameters that approximates some function that we don't know, but we have examples of it for different training data. The learning problem consists of minimizing something. So this is what we call the loss function, the thing that we minimize. So that's a very important term, loss function. So usually machine learning has something to do with optimization, and very often we describe the learning problem by defining a loss function. And the loss function is something where we can get a lot of physics into. And sometimes the physics will tell us what loss function we should be using. So here we just minimize some residuals between the predictions and the true function values, or the function values that have been sampled. They might not be true, they might have some additional noise to them. I'll come to that later. So these are residuals, and we just want to do linear regression, so straight line. Okay, so now we have to define the loss function a bit more. We have to say how exactly we want to quantify error using these residuals. So one way to do this is to use some sort of norm, like a 1 norm or a 2 norm. And here we shall be using 2 norms, so that's just the least squares regression. So we minimize the square differences. Okay, so that's loss function or cost function. We use both words. Most softwares use loss function as a convention. Of course, sometimes we have to maximize something like a score or a merit function, and then we just minimize minus that function. So minus the score is the loss function. Typically, we write all the data into a matrix or a tensor, so just a multi-dimensional array. And then in this case, we'll just have data vectors of dimension little n, and we have capital N many of them, so we'll just put everything into a matrix. And if we regress to one value for each data point, this is going to be a vector, but in general this is going to be a matrix as well of labels that we are regressing to. So this is the training data. It's a pair of two multidimensional arrays. And in general, we have some parameters. We often call them theta. In this case, theta will be just a vector, w, with the regression coefficients. Or for multidimensional regressions or regression to multiple dimensions at the output, this would be a matrix. Okay, least square regression means we minimize this mean square error here over all the data points. And since 1 over n is just a constant factor, we can ignore it when we write these expressions. So this is the loss function that we're going to minimize. All right. In the same way as saying we minimize the square errors, we could give this in a statistical interpretation. Now, this is very interesting from a physics point of view because sometimes there are physical reasons why this actually will apply. So if we assume that there is a function, so if we assume that the predictions are distributed around the true values, and there is an uncertainty, and this uncertainty has a Gaussian distribution, and you can get a similar interpretation if you say there's a true function and I probe this true function with some measurement error because I have some device and this device is subject to many influences, and because of central limit theorem these will somehow average out and manifest themselves as a Gaussian error. Then I can basically ask what is the maximum probability solution subject to this statistical model. And if I assume that measurements are independent, this is just a product of the individual probability densities under this emission probability. And since I don't like to work with products, it's much easier to work with sums. We're just going to logarithmize this function. And, sorry. Then we will get this expression here. So we maximize the sum over these square errors plus or minus some constant factor that we can neglect, or we minimize the mean square error. So the maximum likelihood in the Gaussian probability model is equivalent to the least square error. And in many cases we can find a statistical interpretation for maybe otherwise non-statistically derived loss functions. Yes?
So in your Gaussian, you assume that all the components are IID.
Yes.
And reverse at 1, which is common, I think, in machine learning, but in physics or so, we often have correlations.
Mm-hmm. Yeah, so of course you can insert a covariance matrix here. This is for one-dimensional anyway, but in general you can insert a covariance matrix here.
Yeah, I don't understand why you're assuming that the model already has Gaussian errors. I thought you don't know what the errors are. Are you actually maximizing?
So I'm just saying here the least square error loss function is equivalent to assuming that there is a Gaussian error model on the measurements. You get the same expression. Whether that applies or not in a specific case is an entirely different question. But it is, if you know nothing else, it's a very meaningful assumption because the Gaussian distribution is the maximum entropy distribution if you only have a mean and a variance. Okay, linear least squares regression. So this was least squares regression, so you could still use any kind of function to make the prediction. Now we're going to simplify it even more and say we have a linear model. So we have some basis set. In this case, the basis set is just going to be the features themselves, the input features x themselves, and we're gonna multiply them with some weights. So linear model in the input, as simple as it can get. And in this case, we can just write down the prediction in this form or in a matrix vector form in this way. And then the least square regression problem is just minimizing this this vector norm here of the vector of errors. Okay. Of course, this is very restricted because it's linear in the input. So we can turn this into a nonlinear regression by saying instead of working in this space, we work in a feature space. Feature space means we use some functions, feature functions, or sometimes called basis functions in mathematics usually. And these are nonlinear functions, but they are fixed for the time being. And we just evaluate our actual inputs or the actual recordings in these functions. And the result will be called then the features. And so we will do a linear regression on those features, but those features are nonlinear in the inputs that we start with. So it's a nonlinear method in this way, but it's still mathematically a linear problem because phi are fixed functions. So we only have to solve a linear algebra problem. So it's simple. And the same will be true with kernel regression. Kernel regression is based on the same idea, just that we use an additional trick in order to essentially use more powerful functions. Okay, so this is the form of our linear regression model that is nonlinear in the inputs. And so, for example, if you have a quadratic function such as this, if you have the right features, like 1 for the constant function r and r squared, then this is a linear regression problem. So there are nonlinear functions that you can exactly solve or exactly represent with linear regression if you have the right features. And in many ways, this is the spirit of how deep neural networks work as well. Of course, deep neural networks are very nonlinear regression machines if you use them for regression, but you have these multiple layers that transform the input multiple times. And then the aim is that at the end, after many transformations, you have something that you can express in a simple way. You can write down the regression in a simple way. All right. How do we solve this? So in general, we will write down loss functions and define the machine learning problem in this way. But oftentimes we will not be able to write down a solution or an explicit estimator that optimizes this function. In linear least squares, or in general in linear methods, we can do that because it's just linear algebra. So in this case, the optimal solution, so the solution W, which minimizes this loss function, yes?
There are people of choosing basis function. They're like
I will come back to that later. So in this case, the optimal vector satisfies these equations here. Those are the normal equations. Basically, the idea is if we are in the space of all possible solutions, since we want to minimize the error vector, we want to find the point on the linear subspace of possible solutions that is as closest as possible to the point y. So the point y defines our measurements in a vector space. And the solutions that we can represent with our basis functions defines a subspace, a plane in this vector space. Okay, if we're lucky, y lives on this plane. Then we can achieve error 0. But in general, this is not the case. Then we want to find the point that is closest as possible to y. And the vector, so the error vector of our solution to y is a normal on that plane. This is why these equations are called normal equations. So we're looking for the point where this normal vector starts. Okay, there are some conditions when we can solve this. The formal solution is given by this pseudo-inverse. So we just invert x transpose x. That's a covariance matrix. This is a very bad idea. Don't do this because this is numerically not stable. But it's useful to write down the solution because it has an interesting form that will appear many, many times in other problems. And we can here define two covariance matrices. This is the covariance matrix of the features with themselves. So that's the same covariance matrix that you use for principal component analysis, for example. And this is the covariance matrix of the features with the labels. So we can write down the solution for W as a function of these two covariance matrices here. Okay. Right. So now I want to relate this to a problem that seems entirely different. So this linear least square solutions appear very, very often, even if it seems that we don't have a regression problem to begin with. So I want to relate to some of my work. This is what we call a Markov state model. It's a model of the dynamics of a molecule. And so the idea here is that you have this, you have molecular dynamics, so you have the dynamical motions of a very high dimensional system. These are simplified representations, so there are many, many atoms under this representation that you don't see explicitly. And they kind of wiggle around and move in time. And the idea is that in this very high dimensional space of the positions of all the atoms, that could be like 100,000 dimensions or so, perhaps we can get a reduced representation of the dynamics, which is just a Markov chain, so a discrete time, discrete space, Markov jump process between sets in this space. Now, of course, the sets are some very high dimensional things in this space, right? So if you think about drawing boundaries or clusters, it's something incredibly complicated and high dimensional, and it's not clear a priori how we would find that. But so that's the idea, okay? And it turns out that despite the fact that this is an unsupervised learning problem, how to optimally find that, we can reformulate it as a supervised learning problem, and we'll find that it's actually the same solution as a regression problem. Okay, this is something I need to do later. So I need to switch back. Ah, I was hiding there. Okay, so what we can do here, and this is not just for molecules, but in general for dynamical systems, we can do the following. So our dynamical system is characterized by some coordinates x. Apologies, I should have used r to be consistent with this last slide, but so we have some coordinates to begin with. Let's say the positions of all the atoms, or in a fluid, you could use some sort of density or pressure profile evaluated on voxels in a 2D or 3D space or something like this. And then you project these onto, or you evaluate feature functions on these. So again, you have the freedom to turn this into some nonlinear feature space. And you define these two matrices. So these two matrices are just the whole time series evaluated for all the feature functions at every time step. And the difference between x and y is that they are time shifted with respect to one another. So y is time lagged with respect to x. Tau could be 1, but could be something larger. That depends a bit on the application problem. Now we solve this regression problem, same you saw before, but now multi-label regression. So we regress to a multi-dimensional space instead of to just one value, because our y matrix actually has the same number of dimensions as x. We solve the regression problem, so we approximate the parameters k. This is a matrix, number of features times number of features now, which approximately describes this equation here. Or for every time step, we could say k is the matrix which approximately predicts xt plus tau from xt. And that is, of course, the same solution, the same form of the solution. So it's the pseudo-inverse with these two matrices here. Or just the covariance matrix of X inverted covariance matrix XY. And this covariance matrix XY, because these data are time-lagged, is the time-lagged covariance matrix. So you look at the covariance matrix between a feature now and a feature at time tau later. And this is the instantaneous covariance matrix. And this sort of solution appears many, many times in various methods that have popped up in different fields, like Markov state models, TICA, extended dynamic mode decomposition, etc., etc.
So that in this case, this Koopman operator restricted to the span of the feature functions, right? And goes with the projection.
Yes, yes. So you can get there with Koopman theory or in other ways, like transfer operator theory, etc.
So the feature matrix that you generate has full rank in your case?
It has rank. It has rank n.
Okay.
Yes, and if it is not, of course, I don't do this, but I regularize it somehow. But I've just skipped over this for now because regularization is something I'll do later. Yeah. So, but in general, as I said, don't do this. Yeah. I mean, this is not a good idea to invert a big matrix without regularization. Okay, Markov state models, what I mentioned before. So we actually want this probabilistic model. We are in a state at the current time. What is the probability we will go to another state a certain time tau later? So we can do this in the same way. We just have to define the feature functions appropriately. So if we define the feature functions to be characteristic functions, so functions that are 1 on a particular set in this high-dimensional space. How we find that, different question that comes later. But 0 otherwise, so they're indicator functions. And we just insert, well, let's see what we have as covariance matrices then. So the covariance matrix of the features with themselves, so the instantaneous covariance matrix, because these are indicator functions, they are mutually exclusive. So you can only have one at one of the functions, but not at another one. Or we designed them to be mutually exclusive. Yeah? We designed this to be a full partition of the state space. So that means only the diagonal in this matrix is populated, and it just counts the number of time steps we have been in that state. And the time-lagged covariance matrix just counts the number of times we have seen a particular transition in a time frame of tau. So if we insert this into the solution, we just get that transition probability is the number of times we have seen that transition divided by the number of times we have been in the state I that we start from. And this is indeed it's also equivalent to the maximum likelihood solution of a Markov chain with these observation data if you have no other constraints on the solution. Okay, so here it's interesting to see, so I've mentioned minimum least squares error and maximum likelihood now. So this is one of those problems where you can actually get to the same result in many ways. So you can write different loss functions that will lead to the same estimator. So the minimum regression error on this Markov matrix in this application here. The maximum likelihood, that of course we can only do if we have a probabilistic interpretation, like we would have with these characteristic functions. With the characteristic functions we can say, what is the probability to be there if we have been here, etc. We cannot do this with arbitrary feature functions. Yeah, but if we can do this, we can write down the likelihood function. The likelihood function of seeing this particular trajectory. So basically the history of being in different states at different times. And this is just a probability of realizing every single jump under the transition probability matrix that we have. But because whenever we do a jump between two identical states, I and j, we can just collect these terms. We can also write this as the product overall the transition probabilities in the matrix to the power of the number of times we saw this transition. So this is the likelihood of the Markov chain. And then, of course, we will work with log likelihood again in practice. But so this is the maximum likelihood solution, right? And then there is another principle. That's the variational principle of conformation dynamics. I'll say a few things about that too, which looks a bit complicated right now. I'll explain that on another slide. But the basic idea here is that we do an eigenvalue decomposition of this transition matrix, and we look for the eigenvector space that maximizes the eigenvalues. And I'll tell you in a second why that is a good idea to do. What I want to say on this slide is just that no matter what you use, which of these three solutions you use, you get the same estimator. You can get the same estimator with three different loss functions.
Sorry, I'm lost. What's the connection between P and the problem?
Oh, sorry. It should be K.
Okay.
This is a late night copy-paste thing. Okay, this variational approach. And this really relates to what can physics tell us about what machine learning problem we should be using, or how we should formulate a problem in terms of machine learning. So a little bit of theory about Markov processes. So this is now a continuous Markov process, or continuous space Markov process. We're going to consider discrete time steps, but you can do it with continuous time too. That's not so important here. So the idea is the following. We have a continuous Markov process in this 1D space here. We have trajectories that will evolve stochastically, and they just move around. And the statistics is such that they have, if you run them for a very long time, there will be an equilibrium distribution. So there will be the distribution of points that you sample will converge to something, the equilibrium distribution, and that's the exponential of minus this function. This is the energy function. So in other words, that means we have a high probability of being in the low energy states and a low probability of being at the high energy states. So these four energy minima will be high probability states or metastable states. So they will catch trajectories for a long time, and it will take a long time to transition over one of the barriers and go to another state. And this is the kind of the discrete or the coarse-grained Markov process that we will be interested in. And we can describe this as a propagation of distributions. So we can say there's a probability distribution to be anywhere in this space. This is measured by a function, rho 0, and we propagate this function with a dynamical operator. This is the backward propagator, and there are other classes of propagators we can use. This is called backward propagator. And we arrive at a new function. So this is the distribution at the next time step. And then if you do this many times, we should converge to the equilibrium distribution. Okay? And the core idea here is now that we can decompose this evolution into spectral decomposition. So we can write the same as this function, which is a sum over eigenvectors, eigenvalue terms, or eigenfunctions, eigenvalue terms. This is just some number. This is the eigenfunction. So the eigenfunction is sort of the eigenfunctions define the basis set for this probability evolution. And these are eigenvalues. And you see the eigenvalues have subject to some physical constraints that make sense for some systems, but not for others. This form. So exponential of minus time step times some number that is a rate constant. So that means that many of these terms can be close to 0 if tau is large enough. And that's the coarse graining we do in Markov state models. So we essentially try to approximate this equation by using basis functions or feature functions that can approximate these functions well. That's one part. And the second part is we make time steps in our model that are large enough so that many of these components become 0. And then the problem has become approximate the leading eigenfunctions. Similar like in quantum mechanics. Approximate the leading eigenfunctions, the ones with the largest eigenvectors in this eigenvalues in this case. And because of this relation, the largest eigenvalues correspond to slow or long times, slow motions or long times. So the largest eigenvalues are those that have long physical times associated to them, and they're related to the transition processes across the barriers. Okay. And now this is a purely theoretical description. At this point, this is completely useless because we don't have any of the quantities on this slide in practice. But we know if this is the problem and we want to approximate these eigenvalues and eigenfunctions, we can derive a computational principle that is computable in practice. And that is this variational approach. This is actually the variational approach for conformation dynamics described here, but there is a newer version called VAMP, and that is essentially valid for a more general class of physics systems, let's say. But the bottom line is this is just essentially a formulation of the variational principle of matrix eigenvalues for these dynamical processes and using data. And it says if we want to estimate the dominant eigenfunctions of this dynamical operator, the problem that we can solve to find them is this maximization problem. This maximization problem basically takes feature functions or some candidate functions f and asks how should I design these functions such that I can maximize the time autocorrelation between the functions. And then there are some constraints that make sure that the optimization problem is bounded, so we have to normalize these functions, and then we have to make sure they are orthogonal so that we don't always find the same solution. Yes?
So in the previous slide you had a product in L2. This was L2 of what? It was of rho t of the density at time t, or I mean to be consistent with
this one?
Here, yeah.
This is actually a weighted product over the equilibrium distribution. So this is in a
L2 of the equilibrium distribution.
Yes, yes.
But then the next one, it's not clear that this doesn't depend on t, right? I mean
that what doesn't depend on t?
Expectation at time t.
Mm-hmm.
So
it's over t. Yeah, the expectation is over t. As a time expectation, okay. And so this is valid if for ergodic systems where time and ensemble expectations coincide.
Can you say one more time the connection between the eigenfunctions and the energy line?
Oh, I'm sorry. So in this system there are 4 long-lived states, and there are also 4 eigenvalues that are large, close to 1. One of the eigenvalues is always 1. This corresponds essentially to the fact that there is one stationary distribution. In these eigenfunctions here, this eigenfunction with the 1 eigenvalue is a constant. Right? So it just shows it to be 1, but it's a constant. The other eigenfunctions basically tell you what are the transitions that are corresponding to these long times. So this here is approximately a step function which steps at this point. So that means there is a process where you are long on this side and then after some time you make a transition to this side. So this is essentially a recipe to decompose your high-dimensional state space into chunks, into kind of Markov states. Okay, and so this here is a, despite the fact that we do not know this operator explicitly, we don't have the eigenfunctions or the eigenvalues, this allows us to just evaluate trajectory data, so data, statistics, of simulation data in which we have sampled the operator and maximized this functional and then approximate the leading eigenfunctions and eigenvalues. So this is a case where the physics or the mathematics, depending on how you want to frame it, essentially tells you this is the quantity I'm interested in. Well, if you are interested in the slow processes, usually we are in these applications. And then mathematics tells you this is the function that you can maximize in order to get this result. And so this defines a loss function for you. So this defines a machine learning problem.
Is each function that's independent here? You have the max over...
So because of this constraint, I'm saying here these functions are orthogonal to each other. So they are, they're independent. But you can, of course, deal with non-orthogonal functions and then orthogonalize them. And that will actually, again, lead to the same sort of regression-like result. That is the role then of the feature matrix CXX. CXX inverse basically takes the role of orthogonalizing your features. Okay. All right. And then, well, I have problems finding the... No, it's here. So again, to the role of the different losses. All these three losses, and this is just a reformulation of the variational loss on matrices, so that's the idea. Don't worry about the details here. These three losses achieve the same solution for a fixed basis set. Yeah? If I fix phi, I get the same result, no matter if I minimize this or maximize either of these two. So it looks like it's irrelevant which one I use. Then, of course, I used a simpler one, which is this. But if I change phi, the story changes completely. If I allow to learn phi as well, and that's very important because, as I said, these are high-dimensional spaces, so I have a priori no idea of where the relevant states are, where I should draw the boundaries, etc. Then the problem is that the two first losses that I mentioned, the minimum regression error and the maximum likelihood error, just collapse to trivial solutions that are useless. So minimum regression error, this one, if I am allowed to change phi, I basically am allowed to change x and y, because x and y are the matrices that evaluate phi on the data. So I can always find a simple solution that minimizes this error to 0 by, for example, projecting always to a constant function.
How many different types of phi did you try?
This is just a theoretical statement. You can always define phi to be constant, like 1, for example, and then this will be 0, and that's the minimum possible.
Yeah,
So it's a useless loss if you optimize phi.
no, but did you try different functions, like non-linear functions representing phi?
It doesn't really matter if you will find essentially. I mean, the functions that you can represent depend on the features that you give to the regression algorithm. And if you use a powerful regression machine like a neural network, you can. There's this universality theorem that says you can represent essentially any smooth function on a compact set. So you can represent something that is essentially close to constant on your data. So you will be able to represent this function. And that means you can find a trivial solution, and that's a useless solution.
But in your point 3 from the previous slide, you could also, if you drop the assumption that you have n functions, you could do the same thing, right? You could just do a steady state solution, and then that's constant function 1 also. I mean, somewhere that you have n functions.
With one, if you only use one function, you will find a constant one, and that's actually the right thing because the first function is a constant. But then, if you use more functions, you will find the others. So this is just saying essentially be careful with loss functions because they're not all the same, right? So they may be identical in some conditions, but not in others. So maximum likelihood the same. If we put all the points into one state, the likelihood is 1. That's the maximum you can achieve with this function. And but if you use the variational formulation, this works. So it doesn't fall into these traps. So you can actually approximate these different eigenfunctions with the variational loss. And so this is Andreas' work, who is here. And basically the idea here is to use a neural network now, which takes the data, feeds it through some function encoder. So this is just a featureization basically. And then on this featureized data, we evaluate the variational score. And then we can also estimate a Markov state model. And in this case, what this means is in this example, the output of the neural network is just a softmax function. Of course, you can use other functions if you're directly interested in approximating the eigen functions themselves. And Andy Ferguson has done some work on that. But here we just use softmax functions. So we basically ask what is the probability to be in one of the metastable states. And this is the function that we're learning. And then the regression metrics you get by regressing yt onto yt plus tau is essentially a Markov model, a Markov state model. So it describes the transition probabilities between states.
Why isn't the solution where the encoder outputs a constant value for yt? Why isn't that a trivial solution to this? Why does the network not produce that?
So yt is if it's a softmax, that cannot be all ones, but oh, you mean constant? Constant could be true. Yeah, because that's not what you're optimizing. So you're not working directly on yt. You're maximizing the eigenvalues of this matrix here.
No, but that would still maximize it, right? The Frobenius norm must be maximized if you don't restrict the size of the eigenstate, the linear span of these things, then you get the.
But you do restrict the size. If you have like four states here, then you have to maximize 4 eigenvalues. And you cannot always find the same eigenvalue.
You must have somewhere constrained that you're spanning a 4-dimensional space, otherwise it will collapse again, as you say.
You have it in the loss function, right? So if basically you're maximizing.
Maximize the Frobenius norm of the restriction of the eigenspaces.
You're maximizing something like this. I mean, I can.
But what you're doing is you're taking your operator, you're restricting it to this finite dimensional subspace that you generate, right?
Mm-hmm.
And you're trying to maximize the Frobenius norm of what you get.
Mm-hmm.
But if you don't restrict the size of that subspace, you will converge to that trivial one-dimensional subspace. Somewhere you must be making these assumptions.
So one of your eigenfunctions is this trivial subspace, but not all of them, of course.
It's through the orthogonalization.
I mean, the CXX inverse is doing the orthogonalization.
But somehow, but you have
Frank had that on a previous slide, I think.
Yeah, the previous slide there was a condition that lambda had rank n.
Right.
But so I don't.
That feature is in the optimization. Right. And then
Yeah.
the black box there, the PT Markov.
Oh.
Yeah. Okay. So, all right. Let's go. How am I doing with time? All right. Back to linear least squares. So this was a bit about loss functions and the relation of loss functions and physics. Now let's go back to linear least squares. So one of the questions that came up was how do we choose feature functions, for example? How do we decide how many do we want to use and which functions we want to use, etc. If we don't do linear least squares, but we use a neural network for regression, of course, we have similar problems, like how many neurons do we use, how wide or how deep should the network be, what activation functions, convolutional or dense, blah, 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 all of these questions. So hyperparameters, basically. These are all called hyperparameters. How do we choose them in general? So for this, very important is the concept of validation. So we differentiate between training data and test or validation data. I'll be a little bit sloppy with the words validation and test data in the next couple of slides. Usually we distinguish these two, but for now let's just call it the data that we train on and the rest that we somehow test or validate on. The idea here is the linear least square solution on a given data set gives us the minimum training error on this particular data set. Right, so if we explicitly call this x train and y train, then the W we find is optimizing this function for these training data. Now we are interested in how our solution performs on other data. And the assumption here, and that's very important, and often this is neglected or it's sometimes hard to actually verify, is that these data come from the same distribution and they are IID. So in many cases we cannot get IID data, in many cases it's not clear what has generated the data and if there are some outliers, etc. So that can be tricky. But that is usually the assumption under all of these validation and cross-validation techniques. So anyway, we have found our solution on the training data, and we just use the solution without further training on the validation data, and we evaluate the error on this validation data. That's our validation error. And the idea now is on hyperparameter selection, such as number of feature functions. They cannot be obtained from the learning algorithm itself, so just by minimizing this function, because I can always make the error 0 by giving enough functions. Right? That's a trivial thing to do. If I make the learning algorithm powerful enough, I can always fit my training data exactly. But that may be horrible in terms of predicting something I haven't seen yet. So I'm overfitting. Right? For example, in regression, I can just use indicator functions on single points. I will have a perfect prediction on the data points, and I have no prediction anywhere else. So I need to do this differently, for example, via the validation error. So the idea is minimize this to obtain the parameters. So in this case, the coefficients of the regression. Minimize this then for each corresponding parameter minimum over the hyperparameters to find the hyperparameters. So this is going to get expensive if I do it literally like this, because I have to solve the optimization problem for each point that I evaluate in the hyperparameter space. But so the idea here is basically with this choice of hyperparameters, we can somehow try to find the balance between underfitting the model, where our model is too simple to represent the data, and overfitting the model, where I'm really good in training data, but I'm doing very badly in predicting anything. And I want to be somewhere here. Okay, so generally, data-based validation means we take our data set, we divide it into training and validation set, we learn the parameters on the training set, get the training error or training loss, and we evaluate this solution on the validation set without further training. Now we need to normalize here with the number of samples because they could be different, so it's relevant that we have the right normalization. And this is the validation error or loss, and we choose hyperparameters such that we minimize the validation loss. This is not the only way to do hyperparameter selection or model selection or anything like that. It's just a very simple and very commonly used way. And the reason for that is, is that whenever I have a machine learning problem with a loss function, I can do this. So it's very easy to apply it to many, many different situations. Whereas more, let's say, advanced or theoretically pleasing approaches like Bayesian approaches, for example, can only be applied in certain model classes. Okay, as I mentioned, the reason for doing this is basically to find a balance between overfitting and underfitting. The training error will always decrease if I make the model more expressive or more complex, if I allow it to have more parameters and fit the training data better. But the validation error or cross-validation error will have an optimum somewhere for intermediate complexity. This is for fixed data size. This is important. Where this optimum is depends on how much data you have. If you have more data, this minimum will shift to the right. So the more data you have, the more complex models you can afford without overfitting. And this is also related to the fact why people have used a lot more linear methods like kernel methods in the past, and using a lot more complicated methods like neural networks, for example, these days. Because very simply speaking, neural networks have their optimum more to the right than linear methods. This is, of course, take this with a grain of salt. This is a too simple statement, that's the idea. Okay, in practice often instead of just doing one-way validation, we do something like cross-validation. So cross-validation means in cases where we're not sure about whether our data comes from a simple or well-sampled distribution, if there are outliers, if there is a particular order in the data or so, we can reduce the problems with that by saying we shuffle the training and test data, first of all, so we just randomize the time indices. And then we do cross-validation. So cross-validation means we split the data into k over non-overlapping parts or folds. And then for each fold, we train on all of the data except for one of the folds, and we validate on the remaining fold. And typically we do this for 5 or 10 folds. And then we compute the cross-validation error as the average of the validation errors over these 5 or 10 repeats. Of course, this is 5 or 10 times as expensive as solving the optimization problem once. Okay, so that's the idea. That's fairly clear, I think. All right. So now, let's talk.
On cross-validation, Frank, it might be worthwhile talking about it. Sometimes people still reserve a test set out that's never seen during any of the training or cross-validation to more effectively measure your error.
Yes.
Probably worth
Thanks.
about that.
So the same issue that you have with overfitting on the training data, you can have on the validation data now in the hyperparameter space. So if you are interested in the actual errors and the performance of your model, if you're interested in this figure, and that is often what is reported in machine learning papers, of course, you want to do that on another data set that you haven't used to optimize the hyperparameters. And that's called test set. So then we have these three sets: training, validation, and test set. Often this is not done, actually. So actually, I think most of the benchmarks in neural networks are actually using like just a training set and a test set, and then of course you tend to get solutions that overfit the problem. Jonas?
There was a recent paper where they actually found holdout MNIST and holdout, I think, Cypher.
Nice.
And re-evaluated whether how much the history has overfitted on the test set, and it's actually not too bad. So
it's not too bad?
Surprisingly, well, it works surprisingly well on the really hard out data.
Yeah. So what's the best performance on Cypher 10?
I mean, I can't recall the number. It was just because there was always the suspicion you overfit all the these benchmark data sets, but it's actually not that much as was expected.
Yeah. But of course, then neural networks with stochastic gradient descent are special animals, because stochastic gradient descent is a sort of regularization too. So in principle, you could fall into that trap here by not distinguishing validation and test set. Okay, can we say something more about the validation errors or the test error? So the quantities, the performance measures that we are interested in, and how they behave. And yes, we can. So there is this discipline called Statistical Estimator theory, which is all about that, founded by people like Vapnik. And the idea here is, now we explicitly say, whenever, this is for regression again, so whenever we make a measurement, y, we evaluate the function that is producing the data in some sense. So the function that we're interested in fitting. But we have an additional error. So whenever we make a measurement, we additionally have a random number here, and then of course there should be a coefficient in front of here. Sorry, because we cannot always assume variance 1, but we assume for now that we have a small Gaussian error whenever we record a measurement. You know, think of this as a physical device making a measurement. There will be some measurement errors. Now we want to learn this function by selecting it from some set of functions that we can represent with our machine learning model, like linear regression in some features we have chosen. And we want to find the best approximation. We will achieve some performance, some sort of validation or test error for given choices of model and optimizer. And the question is, what can we say about this number? What does it depend upon, and what can we do to make it better, in some sense, to make it smaller, the validation error? And okay, so we will do this on the validation error because we don't have the true function f directly. And so generally we will get this type of behavior. So I've previously plotted the behavior of training and validation error for a fixed data set. Now, if we vary the amount of data that we have, we will typically have this behavior. So we add more data, then our training error tends to increase, and our validation error tends to decrease. And it's possible, of course, that this function actually meets 0. In this case, this is, for example, true for kernel methods, and then the training error is always 0. But in many cases, this will not go to 0, and then this finite error that we converge to is called the bias. So this is the best we can do with a given model class. We cannot get lower error with this particular model we have chosen. For example, if we do linear regression, if we choose certain features and these features cannot represent the solution, then it doesn't matter how much data we collect, we will always have a finite error at the end. The difference between these two errors here, that is called generalization gap, and that is related to the variance. So that tells us something about if we repeat the process, if we repeat recording measurement data from our points x, and we repeat doing the optimization and learn the parameters, how much will our results spread? And there is actually one second, there is a trade-off between these two that I'll show on the next slide. Tristan?
Do I understand correctly in your plot that the variance depends on the number of data points, but the bias does not? Or are both these quantities meant to be taken in the limit?
Yes, the bias depends just on your model class.
Okay.
Yeah.
But the variance does.
So that is a quantity that is averaged over many repeats.
Is the bias more or less that distance between f and its best approximation?
Yes,
in the feature?
in your solution space. Yeah. Okay, there's typically a trade-off between the two. So what you can have is a situation like you can have a zero bias model. So an unbiased estimator. That means if you repeat the data collection and estimation process many times and average over them, the mean estimator is identical to the true solution. That seems like a nice property, but it could be that such an estimator has a high variance. And often it does. So there is typically a trade-off. Low bias often means large variance. And that means for a finite data set, if we don't have the luxury of having arbitrarily many data points, we may rather prefer a solution where we have a finite bias but a smaller variance. So a smaller spread between solutions. So you can always be, of course, in an individual case, when you record data once, you do the estimation once, you get one of these x's and you might be lucky, but we're interested in the average solution here, in the average situation here. Okay, so that's what I just said. Okay, so now let's look at how bias and variance go into this validation error. So we're interested in this quantity here. So comparison of the predictions on our validation data with the measurements. And remember, those measurements have some intrinsic noise to them. Every time we make a measurement, we evaluate the true function f that we're interested in plus some random noise term. But we don't have access to f directly, so this is what we can work with. Okay, and the idea now, so kind of the algorithm or the thought model that we work with is the following. We take a fixed set of features, xi, so fixed observation points, and then we repeat the following experiment. So we record data on these data points, on these features, and we call this training data. Then we train our estimator on this training data. Then we repeat the experiment. We use the same features. Again, this is not what we usually do when we do cross-validation or something like this. But in this case, because our model, the data recording model says whenever we make an observation, we have this random noise. These will be different. Y train and Y val will be different. So we use this to compute the validation error. Okay, and now we average over many repeats of this experiment. So we're interested in this average here. And now I'm asking, how does this average look like? Can we say anything about the form of this except for this equation? And indeed we can, just using some simple linear algebra and using the fact that whenever we make a recording, it's function f plus some random noise term. So we effectively have to average over the noise realizations. We can decompose this into three terms: bias, variance, and noise. And they look as follows. So noise is the expectation over the difference of the function that we are interested in, this function f, and the recording. So this difference is just this Gaussian random variable that we add every time we make a measurement. And this is intrinsic to our physical or whatever process which generates the data. So this is outside of our learning problem. We cannot do anything about this term. It's just essentially, on average, a constant which is added to the loss. Okay, so this is the noise. And there are cases where we don't have this. So for example, Anatol talked yesterday about machine learning of potential energy surfaces in quantum mechanics, whenever we make a measurement under our quantum mechanical theory, DFT or whatever it is, we just evaluate a function. We don't have this noise. But in many, many cases we have this. Then we have the variance and the bias. So the bias is basically the difference between the function f and the mean over many estimates.
Excuse me.
So the mean estimator, yeah.
Since you just mentioned this,
Yeah.
don't interrupt, but there's actually one method, the quantum Monte Carlo method.
That's true,
And you wouldn't have known.
because you have sampling error. Correct, yeah. Okay, so that's the bias. That's the difference between the function that we are seeking and the mean estimator. And the variance is basically just the variance of estimators. So the difference between the current estimator and the mean of the estimators, averaged over. Okay, and so in practice we always have to play with these two terms. We cannot do anything about the noise, but by choosing the model one way or the other, we can make the bias larger or the variance larger, and of course we're interested in just minimizing this quantity, so we'll have to balance these somehow. Yes?
I
I mean, I think that's not really true anymore for deep learning, right? Because you interpolate your data, get a training plus 0, and then you go into your bias. So bias is always 0. I mean, for shallow stuff maybe, but in the world of deep learning, I think this refers to the same not true or stable.
I think it's still holds, it just does not appear as severe as it was expected. So empirically it's surprising, but I mean, of course, it's still holds.
No, but I mean, your bias is always 0, right? Or on the training data at least.
No.
It's not clear that functions are powerful enough to actually, I mean, if you look at the definition of bias, right, is the function powerful enough to exactly represent the thing you want? Right? Even though we build these ridiculously complicated models, it's not clear you actually have that, right? Look at these things we're approximating quantum mechanics, right? Right? We probably actually don't have a complicated enough computational thing there to exactly redo it. So I think you still have a bias term.
Okay, but I'm not sure like this that I try to find a model which still tries to balance between bias and error.
But it's still useful to find a bias term. Otherwise, you would never do convolutions, but always do dense networks, right? You have more parameters, you can reduce your bias, so always use dense. But it's useful to do.
There are some theories that say that more than twice the number of parameters and data, you can have a So there are theoretically.
Yes. But that's not necessarily the best solution for your validation loss, right?
I mean,
like, for example, parameter, sorry?
No, so there are different ways of actually achieving good generalization.
Yes.
And this is a classical way with fewer parameters than training bias for variance. But there is another way that is actually discovered recently, which actually is not based on penalizing parameters. Like having more complexity.
And what's the idea of this other way? I didn't get the too complicated to explain.
The rest of the time to explain. I can give reference. It's actually a very novel.
Okay, thanks.
But I think we have entered a world where just, I mean, just
trying to explain why they work.
Yeah, I mean, just counting parameters is not sufficient anymore to think about where you are in this bias variance trade-off as we built these more complicated models that have, as Frank said, weird regularization because of how we fit them and all kinds of stuff. So, yeah. I agree.
Okay, so this I've mentioned already. All right, so so this is typically the situation we are in. I wanted to give you, what's the time? Okay, that works. I just wanted to give you an example for that. Again, from our work, that's something that Julia mentioned yesterday. So it's about coarse graining. And again, we start with the kind of the physics formulation and ask what is the machine learning formulation then that we want to use. This is about coarse graining of molecules in structural space. So we want to group atoms together to particles that correspond to multiple atoms. And we want to learn a reduced model that shares some features with the underlying model, the atomistic model. And first of all, we have to define what those features are, what it is that we want to maintain or preserve. And the idea here, that's the physics idea, is thermodynamic consistency. You can also say it's a mathematical idea. Simply speaking is you, and for now we shall refer to coarse graining as application of functions that reduce the dimension of R, and you get X. And these functions for now shall be just linear functions. So it's just be a matrix which essentially coarse grains the R vector into some lower dimensional X vector. It could be a matrix that groups atoms together. That would be one such linear operation. Okay, and the physics idea here is called thermodynamic consistency, and the mathematical idea is just, well, the underlying simulation has an equilibrium distribution defined by this potential here. So e to the minus v of r, that's the probability distribution that this atomistic simulation will sample from in the long run. And I want to preserve that in some sense, but I cannot preserve it on R because I don't have the high dimensional vector anymore. I've reduced the vector. So what I can do is I can preserve the marginal distribution. Right? So I just want to have a new model which gives me an equilibrium distribution that is identical to the marginal distribution of the original model on X. Or written with energies as basically I want to have an energy in the reduced model which is related to an equilibrium distribution that is the marginal of the original. All right? So, and this is then called a free energy. It's the free energy generated by averaging all of the degrees of freedom out that are not included in X. So in the example of a molecule where maybe I also have a box with solvent molecules and ions and other things, for example, if I just throw away the solvent, then I essentially have to average over all of the configurations of the solvent, or over many enough configurations of the solvent for a given coordinate set of the solute, of the molecule. That didn't sound good. Okay, so I want to find the free energy. Unfortunately, this is a little bit tricky because I don't have a direct way to measure the free energy. This is different from like learning potential energy surfaces, where I can just evaluate the potential energy function for some examples and then train my model on them. I don't have this here because computing the free energy involves doing these integrals, and that's hard. So a priori, this is an unsupervised learning problem. So I have to find a formulation of that problem that I can work with. And very important idea is this. It's basically saying, so behind this equation there are actually two ideas. One idea is I can achieve thermodynamic consistency as follows. I can compute the gradient of this potential here, or minus the gradient of this potential. That's a force. That's the force generated by my coarse-grained potential. And this coarse-grained force is, when this is fulfilled, this coarse-grained force is identical to the mean instantaneous forces in the atomistic space. Coarse-grained using this function. Yeah, so I average over all the solvent, take all of the solvent configurations here to the same molecule configuration. I compute the forces in this full space. I project them down to the low dimensional space, so I just evaluate the part of the forces on the molecule and I average them. This is when this is identical to the force computed on this coarse-grained potential, then I have thermodynamic consistency. That's not trivial to show, it's just a result that I'm reporting. Okay. And the second important idea is I don't have to do this weird conditional average, where I average over solvent for a fixed molecule configuration, because that would be really hard to do. I can actually do this, just replace this by an ensemble average over the equilibrium distribution. And combining these two ideas, I can say, okay, this is the quantity I want to minimize. So that's, again, physics or mathematics, no matter. Either way, telling me this is the quantity, this is your loss function. And this turns, I mean, this is one way to frame the problem. There are other ways to try to directly do density estimation and do unsupervised learning on this problem. But this is turning the problem into a supervised learning problem, because we can compute the forces on individual atomistic realizations. So now it's a supervised learning problem. And that's much easier in general. Okay, but we have, again, the same kind of decomposition of the error. This is basically regression. So our error decomposes as the model error and a noise term. And in this case, the noise term is actually quite dramatic, because the noise term contains the fact that we have this high-dimensional atomistic system, and we average out many coordinates, and we keep only a few of them. So the noise term comes from all of the fluctuations of the force due to all of the degrees of freedom that we throw away. So it's a large noise term. So that means we have to have a lot of data in order to overcome the noise, or have a good signal-to-noise ratio, so that we're actually minimizing a meaningful error and not just a noisy error surface. So the composition is the same. Okay, this is the network to do it. Maybe we can talk a little bit more about that tomorrow, about the tricks in here that are useful to have the right physics in the network. Briefly speaking, this network does featureization, which makes sure that we're learning an energy that is invariant to rotation and translation of the molecule. And then it computes its own gradient from its energy in order to make sure that we have what's called a conservative force field. So a force that is computed as the gradient of a potential. And this restricts the possible solutions to those that are physically meaningful for this problem. And then we are regressing essentially these predictions onto our force labels. And so here you see these are cross-validation results. So here you see the validation error, the cross-validation error for this system. We take this small alanine dipeptide molecule in a solvent box, and we throw away all of the solvent and some of the solute atoms, and we end up with just 5 particles. And so basically now we're asking, how does the model perform for different network depths? And if we compare networks with a spline model, this is basically like a shallow learning method. So first of all, you see the network can learn, can get better validation error. And we have to have a certain depth in order to essentially be at a plateau. Potentially it will, for very deep networks, eventually increase, whether that's really overfitting or whether that's just being unable to fit anymore unless we use like ResNets or something like this is a different question. But these are the solutions we can choose. But if you look at the numbers here, you'll see that the differences are relatively small, and there is a very large offset. So this is 384, this is 385. So this offset is just a noise. So in this case, we have a large data set of 1 million data points or something like this. If we use a lot less data points, we have a problem here, because our loss function basically becomes so dominated by the noise and by the fluctuations that it's actually hard to optimize the problem. So noise can be a big issue. Okay, so essentially okay, I need to mention one thing, and that's regularization. So regularization is very important in these shallow methods and for kernel methods. In neural networks, we often regularize differently, but there are cases where we want to use regularization because we're interested in certain structures of the solution. So basically, regularization refers to any kind of technique where we reduce, we somehow limit the space of solutions in such a way that we reduce the prediction error, but we don't reduce the training error in general. And in regression, for example, a typical scenario that we have is that we add a term which penalizes certain weights. So, for example, we may have something like we may penalize the L2 norm, so the squared norm of the weights. Then this is called ridge regression or Tikhonov regularization. We may penalize the 1 norm or even the 0 norm. The 0 norm is basically trying to enforce zeros in the solutions, sparse solutions. I suppose Steve will talk about this at some point. Where's Steve? Not here. L0 regularization is really hard to work with, so people instead typically use L1 regularization, where you just where you just penalize the sum of the absolute values of your weights. And so a very common thing to do if you do normal regularization is ridge regression. So we add this L2 term, and then we can still write down the solution for the coefficient vector. It still has this form, but now what we basically do is we have to add a little diagonal term to the covariance matrix of the features. So basically, you can think of it this way. If your feature covariance matrix doesn't have full rank, so this is supposed to be a symmetric positive definite matrix, but in practice, of course, it can have 0 or almost 0 eigenvalues. Obviously, that's the case if you have linearly dependent features, then you will have 0 eigenvalues. But even if you just have a large matrix, basically, if you have many features, then in practice you will have many zeros or near zeros. And basically, this term is just shifting them away from 0, and this thereby essentially also shifting the eigenvalue spectrum away from 0. So and then we can invert this matrix and evaluate the terms. Okay, these are sparsity-inducing regularizations. I will not talk about this now. And I will also not go into the details of kernel regression. Maybe Anatol does that? Do you? Like this? Okay. Just to give you this one idea. So if we do feature regression, we have to define our features explicitly. We have to say these are the functions that we want to use to evaluate our data points on. And this defines the solutions that we can represent. The idea of kernel methods, so kernel regression, for example, is to say we don't do this explicitly. We say, okay, there is a feature, there is a set of features somehow, but implicitly defined. I am using the so-called kernel trick that allows me to work with either of these two matrices. So either I can do the feature, the matrix which takes scalar products in feature space, or the matrix which takes scalar products in the number of data points. And this can be an advantage if I want to consider very high-dimensional feature spaces that are higher dimensional, that I have data points. There may be feature spaces that are infinite dimensional, and then I can't do the scalar product in this space. But because there's the kernel trick, I can use this other matrix, the kernel matrix, which is number of data points times number of data points, and I can do kernel ridge regression, which uses this matrix. And it can be written in this form here. And this basically says, I can now xi are the the featurized data. I can write down my coefficients as a superposition of feature vectors of the data points that I have. So I'm always restricted to the feature space of the training data, even if my feature space is infinite dimensional. And I can compute the solution and predict values for new points only using this kernel matrix. And so I actually don't have to define phi, because I never have to evaluate it. I can just implicitly define it by defining the scalar product. And this is the kernel function. So it's kind of like, I'm doing this backward. I'm just giving a model of my scalar product and I could use some Gaussian function for that, for example, and that implicitly defines a feature function, and I may or may not know what that feature function is. But there are examples for kernels where I can have relatively simple kernel functions, but implicitly I define an infinite dimensional feature space, so I can do very powerful regression with that. And yeah, and with that I want to finish. Skip the polynomial kernel stuff, and yeah, that's it. Thank you.